Dear students, after studying this module, you shall be able to understand the concept of infrared spectroscopy and predict the number of fundamental modes of vibration of a molecule. The most frequent spectroscopic technique used by organic and inorganic chemists is IR spectroscopy or infrared spectroscopy. It deals with the absorption of radiation in the infrared region of the electromagnetic spectrum. Now, IR spectrum gives sufficient information about the structure, that is, it is helpful in the identification of functional groups of a particular compound, and it can also be used as an analytical tool to assess the purity of a compound. Now, students, the absorption of infrared radiation by a molecule causes changes in their vibrational and rotational energy levels, and hence IR spectroscopy can also be termed as vibrational rotational spectroscopy. Unlike UV spectroscopy, which has very few peaks in their spectrum, IR spectroscopy provides spectrum with a large number of absorption bands and hence provides plenty of information about the structure of a particular compound. Now students, there are different bands present in the spectra or in the IR spectra which correspond to various functional groups and bonds which are present in that particular molecule. Now, the infrared spectrum can be divided into three main types of regions. First of all, the far infrared region, which is less than 400 centimeters inverse. Now, centimeter inverse is the general term or the unit which we use in case of infrared spectroscopy. Second is the mid infrared region, which ranges from 4000 to 400 centimeter inverse, and the near infrared, which ranges from 12,500 to 4000 centimeter inverse. Now students, the mid IR region is of greatest practical use to an organic chemist, but the near and the far infrared regions also provide suitable information about many compounds which can be useful in their detection. Now coming to the mid IR region first, the mid infrared spectrum extends from 400 to 4000 centimeter inverse and results from vibrational and rotational transitions of a particular molecule. Now, this region is most useful for the organic chemist since most of the organic molecules absorb in this range of IR. The mid infrared region can be divided into further two regions. First one is the functional group region, which is from 4000 to 1300 centimeter inverse, and the fingerprint region, which is from 1300 to 600 centimeter inverse. Functional group region, as I told you, it ranges from 4000 to 1300 centimeter inverse. Now most of the functional groups present in the organic molecules exhibit absorption bands in the region 4000 1300 centimeter inverse. Hence, this is known as the functional group region. Now in this region, each band can be assigned to a particular deformation of that particular molecule, the movement of a group of atoms or the bending or stretching of a particular bond in that particular molecule. Next is in the same the fingerprint region, which ranges from 1300 to 600 centimeter inverse. Now the region from 1500 to 600 centimeter inverse usually contains very complicated series of absorptions. These are mainly due to molecular vibrations usually bending motions that are characteristic of the entire molecule or a large fragments of the molecule. Except enantiomers, any two different compounds cannot have the precisely same absorption pattern in this fingerprint region. Thus, absorption pattern in this region are very unique to any particular compound. That is why it is also called the fingerprint region. Now, as you also know, fingerprints are unique to every person existing on this earth. That is why this region is also termed as fingerprint region. It is very difficult to assign individual values in this region. Two molecules having the same functional group but different bonding arrangements may show similar spectra in the functional groups, but their spectra differ in the fingerprint region. Therefore, both the regions are very useful for confirming the identity of a chemical substance completely. This is generally accomplished by comparing the spectrum of an authentic sample. Now, when two compounds show a good match between the IR spectrum in all frequency ranges, mainly the fingerprint region, this strongly indicates that they have the same molecular structure. Now, to understand this particular point, let us take an example of two compounds, that is propan-1-ol and propan-2-ol, that is primary and secondary alcohols with 3 carbons. Now, both the compounds are alcohols and contain exactly the same bonds. Now, if you compare the infrared region of these compounds, the functional group region is very similar for both the compounds as they both are alcohols, but the fingerprint region is totally different. Therefore, fingerprint region could be very crucial to identify the compound and its type of bond. This is clearly exhibited by the two figures shown to you. First one is of propan-1-ol and the second one is of propan-2-ol. Now, coming to the second region, as we described earlier, the near infrared region, it ranges from 12,500 to 4,000 centimeter inverse. The absorptions observed in the near infrared region, that is, again I would like to mention 12,500 to 4,000 centimeter inverse, are overtones or combinations of the fundamental stretching bands. Bands in the near infrared region are usually very weak in intensity. They are often overlapped and hence are less useful than the bands in the mid infrared region. Now, we will come to know about the overtones and combinations and the fundamental stretching bands later in this module, students. Now, the near infrared region, also known as the NIR, shows some similarities to the UV visible spectrophotometry and some to the mid-IR spectrophotometry. Indeed, the spectrophotometers used in this region are often a combination of UV visible and near IR ones. Now, near infrared region is generally used for quantitative organic functional group analysis. The NIR region has also been used for qualitative analysis too and studies of hydrogen bonding, solute-solvent interactions, organometallic compounds and inorganic compounds. Now, far infrared region, which ranges from 600 to 100 centimeter inverse. Now, the far infrared spectrum extends from 600 to 100 centimeter inverse. Organometallic and inorganic molecules contain heavy atoms and weak bonds. Therefore, the fundamental vibrations of these molecules fall in this region. Lattice vibrations of crystalline materials occur in this region too. Now, students, after having studied in detail the various regions of infrared spectroscopy, let us now study about the origin of IR spectroscopy. Now, IR spectroscopy gives the information about molecular vibrations, or more precisely on transitions between vibrational and rotational energy levels. Since the absorption of infrared radiation leads to transition between vibrational and rotational levels, as I have already told you, it is also known as vibrational rotational spectroscopy. Now, when a molecule absorbs IR radiation below 100 centimeter inverse, transitions between rotational energy levels takes place. Since these energy levels are quantized, a rotational spectrum consists of discrete lines. If a molecule absorbs radiation in the range of 100 to 10,000 centimeter inverse, it causes transition between vibrational energy levels. Now, these energy levels are also quantized, but vibrational spectra appears as bands rather than discrete lines. Now, each vibrational energy level is associated with a large number of closely spaced rotational energy levels, or we can put it like this, that the energy difference between various rotational levels is very short than the energy difference between various vibrational levels. Therefore, vibrational spectra appears vibrational rotational bands instead of discrete lines. Organic chemists are mainly concerned with these transitions, especially with those which occur in the range of 4000 to 667 centimeter inverse. Next, we come on to the molecular vibrations. The atoms in a molecule do not remain fixed at certain positions. The two nuclei can vibrate backwards and forwards, or towards and away from each other around an average position. Now, these two types of fundamental molecular vibrations, that is stretching, which leads to change in bond length, and bending, which leads to change in bond angle. Now, let us come on to the stretching vibrations. It involves a rhythmic movement along a bond axis with a subsequent increase and decrease in the bond length of a particular molecule. Stretching vibrations are of two types, symmetrical stretching and asymmetrical stretching. Now, this is clearly shown in the figure. First you are seeing the symmetrical stretching, and in the other one you are seeing the asymmetrical stretching, and this belongs to the water molecule. Second comes the bending vibrations. It involves a change in the bond angle or movement of a group of atoms with respect to the rest of the molecule. Bending vibrations are of four types: rocking, scissoring, wagging and twisting. Now, these all can be seen in the figure. The first one is scissoring or bending in plane. The second one is twisting or bending out of the plane. Third one is a rocking or bending in the plane. Fourth one is wagging or bending out of the plane. This belongs to, all these bending and stretching vibrations belong to the methylene group or the CH2 group here. All the bonds in a molecule are not capable of absorbing infrared radiations, but only those bonds which are accompanied by a change in the dipole moment will absorb in the infrared region. Thus, vibrations which are associated with the change in the dipole moment of the molecule are called infrared active. Otherwise, the vibrations are said to be IR inactive and thus do not show any absorption band in the IR spectrum. Now, generally, larger the change in dipole moment, the higher is the intensity of absorption. Hence, the vibrational absorption bands in simple hydrocarbons are weak, while bands associated with bonds connecting atoms with a considerable electronegativity difference give stronger bands, because then the dipole moment change will also be large. Now, next we come on to the selection rules in case of IR spectroscopy. IR radiations absorbed only when change in the dipole moment of a molecule takes place. Now, complete symmetry about a bond may eliminate certain absorption bands. Therefore, number of absorption bands observed is not exactly equal to fundamental vibrations. Some of the fundamental vibrations are IR active while others are not. This is governed by selection rules described. In a molecule with a center of symmetry, the vibrations symmetrical about the center of symmetry are IR inactive. The vibrations which are not symmetrical about the center of symmetry are IR inactive. Now, here I would like to take some examples to explain the above selection rules. All the symmetrical diatomic molecules such as hydrogen, nitrogen, chlorine, etc. are IR inactive. Secondly, the symmetrical stretching of C double bond C alkynic bond in ethylene, that is having the center of symmetry, is IR inactive. Third, the symmetrical stretching of CO2 is IR inactive, whereas asymmetrical stretching is IR inactive. The fourth point, cis dichloroethylene molecule shows C double bond C stretching bands, whereas trans molecule does not show this band because trans is a symmetrical molecule and cis is a non-symmetrical molecule. Now, coming on to the fundamental vibrations. In the classical harmonic oscillator, the energy is described as half kx square is equal to h nu, where x is the displacement of the spring. Thus, the energy of or frequency is dependent on how far one stretches or compresses the spring, which can be any value. If this simple model were true, as you can see, a molecule could absorb energy of any wavelength. Now, you can see the ideal harmonic oscillator and its energy curve in this figure. However, vibrational motion is quantized. It must follow the rules of quantum mechanics, and the only transitions which are allowed fit formula, which is E is equal to brackets n plus half bracket closed h nu, where nu is the frequency of vibration, n is the quantum number 0, 1, 2, 3, etc. Now, the lowest energy level, that is E0, is equal to half into h into nu. The next would be E1 is equal to 3 by 2 h nu. Now, according to the selection rules, only transitions to the next energy levels are allowed. Therefore, molecules will absorb an amount of energy equal to 3 by 2 minus 1 by 2 h nu, or simply h nu. This rule is not inflexible, and occasionally transitions of 2 h nu, 3 h nu or higher are often observed. Now, these corresponds to bands called overtones. As I have mentioned earlier, it will be explained later. Now, here you can see bands corresponding to h nu are fundamental bands, and those correspond to greater than h nu, that is 2 h nu or 3 h nu, correspond to overtones in an IR spectrum. They are of lower intensity than the fundamental vibration bands. IR spectrum of a compound may show more than one vibrational absorption bands. The number of these bands correspond to the number of fundamental vibrations in the molecule, which can be calculated from the degree of freedom of a particular molecule. Now, a molecule comprising of n number of atoms has a total of 3n degrees of freedom. In a nonlinear molecule, 3 of these degrees of freedom are rotational and 3 are translational, and the remaining that is 3n minus 6 correspond to the vibrational degrees of freedom or fundamental vibrations, whereas in a linear molecule only 2 degrees of freedom are rotational, because rotation about its axis of linearity does not change the position of the atoms, and 3 are translational. The remaining 3n minus 5 degrees of freedom are vibrational degrees of freedom or fundamental vibrations. Now students, if a molecule is symmetrical such as hydrogen, nitrogen and chlorine, the band is not observed in the IR spectrum. Asymmetrical diatomic molecules like carbon monoxide, CO and iodine chloride ICl absorb in the IR spectrum because there is a difference in the dipole moment of the two atoms. It has been observed that in actual IR spectrum, the theoretical number of fundamental bands is seldom observed because there are certain factors which may increase or decrease the number of bands. Some fundamental vibrations lie outside the IR region, that is 4000 to 400 centimeter inverse range, whereas some are too weak to be observed. Few fundamental vibrations are too close that they merge into one another. The occurrence of degenerate bands or bands of same frequency also causes decrease in the fundamental vibrational bands. This phenomena is called as Fermi resonance. Now let us study Fermi resonance. The Fermi resonance effect usually leads to two bands appearing close together when only one is expected. When an overtone or a combination band has the same frequency as or a similar frequency to a fundamental band, two bands appear split either side of the expected value of about equal intensity. Thus, degeneracy is achieved. This effect is greatest when the frequencies match, but it is also present when there is a mismatch of a few tens of wave numbers. The two bands are referred to as a Fermi doublet. For example, Enrico Fermi showed this particular example in case of carbon dioxide, which is a linear molecule and has 4 fundamental vibrations, but actually it shows only 2 bands, that is at 666 centimeter inverse and 2350 centimeter inverse. The symmetrical stretching of CO2 is inactive as discussed before. In the IR, because of the vibration, produces no change in the dipole moment of the molecule. The two scissoring or bending vibrations are equivalent and therefore have the same frequency. They are degenerate at 666 centimeter inverse. The asymmetrical stretch of carbon dioxide gives a strong band in the IR at 2350 centimeter inverse. This can be clearly shown in the figure. Now the appearance of certain types of non-fundamental bands, also known as overtones, combination of fundamental vibrations or difference in fundamental vibration bands, increases the number of bands as compared to that expected from the theoretical number of fundamental bands. All these bands have a very weak intensity than the fundamental vibrational bands. Let us come to now overtone bands. In addition to the fundamental vibrations as studied before according to the selection rules, other frequencies can be generated by modulations of the fundamental bands. An overtone band occurs when the molecule makes a transition from the ground state, that is 0 level to the second excited state to the second level, that is V is equal to 2 or N is equal to 2, where V, or we can say N, is the vibrational quantum number as mentioned in the formula before. The intensity of the overtone band is very low as compared to the fundamental band, and they are usually found in the near infrared region. Now, based on the harmonic oscillator approximation, it has been found that the energy of the overtone transition is about n times the fundamental vibration associated with that of the particular transition. Suppose a compound shows strong absorptions at x and y centimeter inverse, then it may also give rise to weaker absorptions like 2x, 2y, 3x, 3y centimeter inverse respectively. The intensity of overtones decreases as the order of overtone increases. That is, the intensity of 3x or 3y overtones will be less than 2x and 2y overtones. Therefore, second and third overtones are rarely observed. Combination bands. Now, the combination bands are observed when two or more than two fundamental vibrations are excited simultaneously. If there are two fundamental bands at x and y centimeter inverse, then it may also give rise to absorption bands like x plus y, x plus 2y, 2x plus y centimeter inverse. Now, another term is difference bands. It is also possible to have a difference band where the frequencies of two fundamental bands are subtracted, that is x minus y, x minus 2y and 2x minus y centimeter inverse. A practical use for understanding overtones and combination bands is applied to organic solvents used in spectroscopy. Most organic liquids have strong overtone and combination bands in the mid-infrared region. Therefore, acetone, DMSO, that is dimethyl sulfoxide, or acetonitrile should only be used in very narrow spectral regions. Solvents such as carbon tetrachloride, that is CCl4, carbon disulfide CS2 and CdCl3, that is deuterated chloroform, can also be used above 1200 centimeter inverse. Now students, let us summarize this module. Absorption of electromagnetic radiation in the infrared region can cause changes in the vibrational and rotational energy states. Thus, infrared spectroscopy is also known as vibrational rotational spectroscopy. A molecule consisting of n atoms has a total of 3n degrees of freedom, and it may vary from linear and nonlinear molecules. The number of fundamental vibrational bands in a molecule is equal to the degree of freedom of a molecule. However, these numbers of bands is seldom obtained because of the occurrence of certain non-fundamental bands, and they are known as overtones, combination bands, difference bands of fundamental vibrations,